This video is about activity 314, and the problem that we're going to go over models some business information. So you're employed by a company that manufactures solar collector panels. To remain competitive, the company must consider many variables and make many decisions. Two major concerns are those variables and decisions that affect operating expense or cost of making the product and those that affect the gross income or revenue from selling the product. Costs such as rent, insurance, and utilities for the operation of the company are called fixed costs. These costs generally remain constant over a short period of time and must be paid whether or not any items are manufactured. Other costs, such as materials and labor, are called variable costs. These expenses depend directly on the number of items produced. The records of the company show that the fixed costs over the past year have averaged $8,000 per month. In addition, each panel manufactured costs the company $95 in materials and $55 in labor. Write a symbolic rule in function notation for the total cost C of n of producing n solar panels in 1 month. So we have two different types of costs. We have the fixed costs, and that doesn't matter how many panels we make. So our cost is going to be C of n, and this $8,000 we have to pay no matter what. Plus, we have our variable costs that change depending on how many we make, and that's the cost in materials for each panel and the cost in labor for each panel. So each panel is going to cost us $95 for materials and $55 for labor. So we need to add those two variable costs together. 95 plus 55 gives us 150. And then that's for each panel. So for n panels, we would have to multiply that by n. So our cost function is C of n equals 8,000 plus 150n. And it doesn't matter what order you write this in. You could have written 150n plus 8,000 as well. A marketing survey indicates that the company can sell all the panels it produces if the panels are priced at $350 each. The revenue or gross income is the amount of money collected from the sale of the product. Write a symbolic rule in function notation for the revenue, R of n, from selling n solar collector panels in 1 month. So R of n is our revenue. Each panel we're going to sell for $350. If we sell n of them, we will have a revenue of 350 times n. And I am going to change the color of this, and actually I'm going to make it blue. So R of n was 350n, and I'm going to change this one to red. Okay, so now we're going to fill in this table, and we are going to plug 0 in for n into the cost function, and then 10 and 20 and so on, and then do the same for the revenue function. So if we don't sell any solar panels at all, our costs are going to be $8,000. And if I sell 10 of them, then I'll have the $8,000 plus 150 times n. And 150 times 10 is 1,500, so my costs are going to be 9,500. And if I sell 20 of them, 20 times 150 is 3,000, so my costs will be 11,000. If I sell 30 of them, then my costs are going to be this 150 times 30, which is 4,500. Add that to the 8,000 and we get 4,500. And so notice each time I go up by 10, my costs go up by $1,500. And so we can just keep adding 1,500. So this will be 6,000 and then 7,500, and then this for 60 will be 9,000. Now we're going to fill in the revenue table. If I don't sell any, I'm not going to make anything, so that will be 0. If I make 10, it will be 3,500. If I make 20, it would be 7,000. If I make 30, 30 times 350 will give me 10,500. And if I make 40, that will give me, let's see, 14,000. And if I sell 50 of them, that will be 17,500. And then 60 times 350 would give me 21,000. So each time I had to add 3,500, or every other 7,000 would be the easier way. Or you can just multiply n by 10, 20, 30, 40, 50, and 60. And I wanted those in blue, so I'm just going to change them all to blue. Okay, so now I want to sketch a graph of the costs and the revenue function using the same set of coordinate axes. So here is my axes, and we just need to count our tick marks so we know how many we have. And I'm going to make my view a little bit smaller so that I can see my graph better. And so I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. 25 in that direction, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 here. Okay, so this is my x-axis, or actually n, and n is the number produced. And this is cost and revenue. So that's C of n and R of n. And this is in dollars. So for the number of panels, we're going to go from 0 to 60. And I have 25 tick marks, so I'm going to let each of these be equal to 5. Okay, well, let's just do this. So we want to go from 0 to 60. If we take 60 and divide it by 25, what do we get? I just want to have it spread out a little bit better. That gives me 2.4. So we'll go up to every third panel. So if we let each of these be 3, that would be big enough, but then that would be then we would be marking every ninth, and that would be weird. So we'll do every third. It just spreads it out a little bit better. So if we did every fourth, we would run off our graph a little bit. Okay, and then oh, I have some mistakes in my table. Let me go back and fix these. This should be let's see, what should these be? So I'm going up by 1,500 each time. So this would be, this one's the one that got me off. So 9,500, if I add 1,500 to that, That's going to be 10, no, that's 11,000. And then add 1,500 to that, 1,250. Add 1,500 to that, 14,000. Add 1,500 to this one, we would have 15,500. And add 1,500 to that, and we would have 17,000. Let me just check those with my calculator. I'm not doing it in my head all that great. So 8,000 plus 1,500. $950, 1,100, 1,250, 14,000, 15,500, and 17,000. So we did that one right. And then 3,500 plus 3,500 gives me 7,000, then 1050, 14,000, 17. All right, so now all my numbers are okay. So we need to go from 8,000 to 17,000 for the cost function, but for the revenue function, we have to go from 0 all the way up to 21,000. So on our graph, we need to have the largest range. We need to incorporate any numbers that are in this table. So we need to go from the 0 all the way up to 21,000. So over here, 21,000 is how big I need to go. And we need to divide that by how many tick marks we have, 19. And so we get 1105. And really you'd have to go up to 1106 to make it fit on your graph. And up here we went up by 3,500 each time. So if I divide that by 2, what would I get? And is it bigger than this? So 3,500 divided by 2 gives me 1,750. So I'm going to go up by 1,750 or 3,500 every other tick mark. So we'll keep all of this in blue. 0, 3,500, and then 7,000, and then 1050 or 10,500, sorry. And then we want to go up by 3,500, so that's going to be 14,000. And that's, let me move this stuff. And it's going to need to go up even further there. All right. And so that's going to be 17,500, and then our last one is 21,000. So doing this calculation gives you the smallest number that you can use to label your tick marks, but then go back up to your graph or your data points and try to pick something so that your data points will lie nicely on your graph. It just makes your graphing life a lot easier. So our first data point is 8,000, or 0, 8,000, and we did that one in red, so let me switch back to red. So 0, this is 7,000 right here, and we went up by 17,000 or 1,700 each time. So this red graph isn't going to be the greatest, but you'll get an idea. So right here we're going to be at 8,750. So it's going to be right about there. And you don't need to be totally exact on these. And then we have 10, 9,500. So that's going to be a little bit below the 10,500. And then we have 20, 11,000. So here's 20, and so we're going to be right above the 10,500 there. And then 30, 1250. That'd be about right there. And then we have 40, 1400. This one actually is right on the graph, which is nice. And then we have 50, 15,500. And then we have 60, 17,000. So again, these aren't exact because they don't match up nicely. That's why it's nice to have them matched up nicely if you can. But so our next set of data points, I'll plot these ones in blue. So we have the point 0, 0. And we have the point 10, 3,500. And again, we mark these so that these would all lie nicely on our graph. So those ones are easy to plot. Oh, let's see. One got missed. That should be 60, 21,000. Oops. Should have just labeled them as I was marking them. That would have been easier. We'll put that right there. And then also the 50, 1750 we'll put over here too. All right, so there's those. And then marking the other points. Let me go back up and check what the 51 was. 15,500. And here we have 60, 17,000. And then this point was shared. So that was 40, 14,000. All right, so it gets a little bit messy when you're labeling your graph and you have so many data points, but it's nice to have them there so that you can go back and refer to them. And I'm going to switch my pen back to black. Now we want to estimate the break-even point on the graph. And so break-even means you're not making any money, but you're not losing any money either. And remember, this red graph is our cost function. And the blue graph is our revenue function. And so where are my costs and my revenue the same? Well, it happens at this point where they both intersect. And so that's happening at the point 40, 14,000. What system of equations must be solved to determine the break-even point for your company? And the system of equations is C of n equals 8,000 plus 150n, and r of n equals 350n. Okay, so it's the two functions that we had for cost and revenue, because they're going to break even when the costs and the revenue are the same. So now we're going to solve this algebraically, and so we break even when the cost and the revenue are equal. So to solve this algebraically, we just need to set these two equations equal to each other. 350n equals 8,000 plus 150n. And then solve this equation for n. So we'll subtract 150n from both sides. And 350 minus 150 is 200. And then divide both sides by 200. And that does in fact give us n equals 40. Does your graph confirm the algebraic solution in part C? And yes, it does. That was where our two lines intersected. Revenue exceeds cost when the graph of the revenue function is above the graph of the cost function. For what values of n is r of n greater than c of n? And what do these values represent in this situation? So we could have actually have done this algebraically as well. To do this algebraically, we would take the revenue function, which is 350n, use the greater than symbol, and then put the cost function in there, 8,000 plus 150n, and then solve this. The only thing that you have to be careful of is if you multiply or divide both sides of an inequality by a negative number, you have to remember to reverse the direction of the inequality. We're not going to multiply or divide by a negative number though, so we don't need to worry about it. This is just going to stay greater than. So first we had to subtract the 150n from both sides. And that gave us 200n, and this time would be greater than 8,000. And then we divide by 200. And that gives us n is greater than 40. So when n is greater than 40, our revenue will be more than our costs. So when we make more than 40 panels, okay, so when we make more than 40 panels, our revenue will be greater than our costs. And we can see that from the graph as well. Here's our revenue function, and when n is bigger than 40, the revenue function is above the cost function. So you can also see it from the graph here. The break-even point can also be viewed with respect to profit. Profit is defined as the difference between revenue and cost. Symbolically, if P of n represents profit, then P of n equals R of n minus C of n. Determine the profit when 25 panels are sold. What does the sign of your answer signify? So first we could calculate R of n, and that would be, R of 25. So that would be 350 times 25. And we get 8,750. And then calculate C of 25, and that's going to be 8,000 plus 150 times 25. So do the multiplication first. Remember, you have to follow order of operations. So 150 times 25, and then add on to that the 8,000. And we get 11,750. Now take your revenue and subtract from that the costs. Okay, so that's going to be 8,750 minus 11,750, and that gives us negative 3,000. Determine the profit when 60 panels are sold, so do the same thing, only we're going to plug 60 in now. And actually, I think we have those numbers up in our table, so why redo something? So the revenue will be 21,000. And the costs, 8,000 plus 150 times 60 will give us 17,000. Take the revenue minus the cost, that will be 21,000 minus 17,000, and we get 3,000. Oh, and I forgot to answer part of our question. So what does this negative sign mean in terms of profit? It means that we lost $3,000. And here, since this one is positive, we actually made some money. We had a profit of $3,000. So now use the equation C of n and R of n and write a profit function in terms of n solar panels. Sold per month, write the expression in the profit function in simplest form. So it's going to be our revenue. P of n is our revenue function minus our cost function. Our revenue function was 350 times n minus our cost function. So we're subtracting this whole function, so put it in parentheses. So that was 8,000 plus 150n. And simplifying this, we have to distribute this negative sign. That gives us 350n minus 8,000 minus 150n. And if we simplify this, so 350 minus 150 is 200n, and then minus 8,000. And so this is our profit function. 200n minus 8,000. Use the rule in C to compute the profit for selling, and this should be 25 and 60 panels. And how do they compare with our results in A and B? So first let's do it for 25 panels. P of 25 will be 200 times 25 minus 8,000. And 200 times 25 gives us 5,000 minus 8,000. And so we get a negative $3,000. And then do the same thing for 60. 200 times 60 minus 8,000. And 200 times 60, that will be 12,000. Minus 8,000 gives us 4,000. And did I use, what did I do wrong? Oh, well, I just subtracted wrong. That should have been $4,000. Okay, so they do match, and they should match, and that's why I knew that I had made a mistake above, was because my numbers weren't matching. So yes, they do match. So again, just keep that in mind. If you do run across something weird like that, it should cause you to pause, like it did me, and go back up and figure out what happened there and what went wrong. So what do we expect profit to be at the break-even point? Well, that's when revenue and costs are equal to each other, so when they're equal and then we subtract them, we should expect a profit of $0. Use the profit equation to confirm the profit N panels sold in a month is 0 at the break-even point, so we want to calculate P of 40. And that's 200 times 40 minus 8,000. And we do in fact get 8,000 minus 8,000. And that is $0. Okay, that's it for this lecture. Let me know if you have any questions. Thanks.